Okay guys, so this is a recap, or a mini reteach if you want to call it that, of section 2.7, which is on nonlinear inequalities, and this begins on page 178 in the textbook. Okay, so a polynomial inequality is just an inequality that contains a polynomial of degree 2 or higher. It has to be degree 2 or higher because if it's degree 1, that's a linear function. So it has to be degree 2 or higher. And it's an inequality because instead of having an equal sign, it's going to contain a less than, greater than, less than or equal to, or greater than or equal to symbol in it. Okay, so when I went over this originally in class, I first wrote down the steps on what we need to do in order to solve a polynomial inequality. Okay, so the idea is that you're going to take all the terms of the inequality and move them to the left side of the inequality symbol, and make sure that the right side of the inequality symbol is 0. Okay? You're going to factor the polynomial to find the zeros, which are also called key numbers. Okay? So, if you end up factoring and you get 2 zeros, you're going to have 3 partitions on the number line. So after you find the zeros, you're going to put those numbers, those zeros or key numbers, in ascending order, meaning from smallest to largest on the number line, in order. Okay, and what that's going to do is it's going to subdivide the number line into so many partitions, n+1 partitions, and you'll see what I mean by that in a minute. Okay, those are called test intervals. Okay, they're called test intervals because you're going to choose a number from each one of those subintervals or test intervals to plug back into the polynomial to determine where that polynomial is positive or negative. Okay, and then based on your result, that's going to help you determine the solution interval and allow you to graph the solution set. So these are best done by example, so let's do that. The first example I went over in class. So these are just the notes. I just printed them from EDSB, the ones that I had scanned. So these are no different than the notes that are already on EDSB. But the first example I did was x squared minus x minus 6. Well, the first step says to make sure the left-hand side has all the terms of the polynomial and the right-hand side is 0. So we don't need to do that step because this is already in that form, right? So the other thing is I want to make sure on the left-hand side that I'm writing the powers of x in descending order because I want to factor, so it's just going to make my factoring easier, right? And what I notice is that I can factor this little polynomial here. I know that the factors of 6 are 2 times 3, and 3 minus 2 gives me 1. So I went ahead and factored that down. So I got the product of 2 binomials, x minus 3 times x plus 2. And if you're not sure, you can FOIL those back together and you should get what you started with, all right? And what you do here is, you set each one of these equal to 0 and solve for x. So I got x equals 3 and x equals negative 2. So these are the zeros or the key numbers of the polynomial. Okay. Once you have the zeros or the key numbers, you put them on it, just draw a number line and put them in ascending order. So negative 2 and then 3. So just like that. Okay. After that, what you need to recognize is you've got 2 zeros on the number line, and it partitions it into 1, 2, 3 different sections, okay? This section here goes from negative infinity to negative 2, okay? This partition goes from negative 2 to 3, so I wrote it there. And this partition starts at 3 and goes all the way to infinity. So that's how you denote each subinterval or test interval, okay? And the idea is you're going to choose a number in each one of these intervals. And, again, as I said in class, I could check a negative 1 million if I wanted to, or a positive 300, and plug it in to see if it's positive or negative, but that's not necessary. Generally, we just pick a number to the left and to the right of each key number. Okay, so what I chose here was my test numbers that I'm going to plug back into my polynomial. X equals negative 3, x equals 0, because 0 is always easy to compute, and x equals 4. And what you do is you write those down, the test numbers that you're going to use, and then you plug it back into your polynomial. Now you can plug it in here and compute it, But I choose to plug it into the factored form because I don't care if I get a negative 10 or a positive 7. What I care is it negative or positive? I only care about the sign. Okay, so I use the properties of multiplication to help me determine that really, really quick. So I'll show you how I do it. If I plug a negative 3 into this binomial for every x, I'm going to have negative 3 minus 3, right here, times negative 3 plus 2. So what I have here is negative 3 plus, or negative 3 minus 3 is a negative, so I'm going to write this up here, it's a negative 6. When the signs are the same, you add and keep the same sign. And in this parenthesis, I've got a negative 3 plus 2. When the signs are different, you subtract, so 3 minus 2 is 1, and you use the sign of the bigger number. The bigger number is 3, and it's negative, so I'm going to make that negative, okay? And now what I have is negative 6 times negative 1, because this was a product. Negative times a negative, which I have listed here, is a positive. So what I know is that no matter what value I choose, from negative infinity all the way to negative 2, if I plug it into that polynomial, it's going to give me a positive result. So I put a little plus sign there. Now I'm going to do the same thing with the 0. If I plug the 0 in for each x in this binomial, I'm going to have 0 minus 3, which is negative 3, and 0 plus 2, which is 2. And I have a negative times a positive, which gives me a negative. So I know between negative 2 and 3, no matter what numbers I choose between negative 2 and 3, if I plug it into my polynomial, I'm going to get a negative number. I don't care what the number is, I just need to know is it positive or negative. And finally, when I plug the 4 in, I have 4 minus 3 is 1, and 4 plus 2 is 6, and a positive times a positive gives me a positive. So from 3 to positive infinity, any number I choose, you know, if I plug a 10 in here, I'm going to have a positive times a positive is going to be a positive. If I plug 200 in there, a positive times a positive is positive. So I'm going to have positive, negative, positive. My signs are going to alternate, not always, but in this case, about those key numbers or zeros. And what does that mean? Well, my solution is going to be, the hint is going to be given to me by the polynomial. So my coffee cup shadow is in the way there. There we go. Sorry about that. So the key is right here. This says less than 0, meaning negatively valued or negative numbers. So anywhere my polynomial is negative, which in this case is going to be between negative 2 and 3, that's going to be my solution. And if I want to graph that, I just shade that in and I cap it off here with parentheses. So the solutions for this polynomial that are going to make this statement true are going to lie between negative 2 and 3, not including negative 2 and 3. And if I were to graph that polynomial on my calculator, what you would see is that, you know, it'd be a parabola, right, because it's a quadratic, and it's going to open up because A is positive. So it's going to smiling parabola, right? It's going to open up. It's going to intersect the x-axis at x equals negative 2 and x equals to 3. All the positive values are always above the x-axis, and negative values are below the x-axis. So these values here are going to make my polynomial true. Okay, it's going to keep it less than 0. Here's another one. X squared minus x minus 20 less than 0. Again, everything's over to the left, 0's on the right, so I can skip step 1. So the next step is I want to factor this, so I went ahead and factored it down. I got x minus 5 times x plus 4, and if I solve each one of these for x, I get x equals to positive 5 and negative 4. So those are my zeros or key numbers. I drew a number line. I put the key numbers on the number line in ascending order from smallest to largest. And I said, ooh, I've got 1, 2, 3 subintervals or test intervals from negative infinity to negative 4, from negative 4 to 5, and from 5 to infinity. So I wrote them down right there. And now I need to choose test numbers. So I tested a negative 5, a 0, and a 6. When I plug in a negative 5, I get negative 5 minus 5, which is a negative number, times negative 5 plus 4, which is another negative number. So I know that a negative times a negative makes a positive. So we're going to have positive or a little plus here. From negative infinity to negative 4, the polynomial is going to take on positive values. When I plug in the 0, now look, I just want to say, this looks exactly like the other one up there. It's not necessarily the same, all right? So just keep that in mind. All of this stuff can change depending on the polynomial. So it's not always plus minus plus, it's not always minus plus minus, it could be plus plus plus, could be a lot of different things, so keep that in mind. When I plug the 0 in, I'm going to have a negative times the positive gives me a negative, so values are negative here. And finally, when I plug the 6 in, I have 6 minus 5 is 1, 6 plus 4 is 10, so a positive times a positive gives me a positive. Again, I look at my inequality symbol right here, so to make this true, my solution has to take on negative, less than, right, 0 values. That's going to be between negative 4 and 5. So I put parentheses here and here and shade in my solution set. Okay, anything outside of that is not going to be a solution. So in other words, if I plug a negative 5 in there, just to show you, do it right here, I would have negative 5 squared minus a negative 5 minus 20. And the question is that less than 0? Well, if I square negative 5, I get a positive 25. The opposite of a negative 5 is a positive 5 minus 20. So again, I'm still wondering, is that less than 0? Well, 30 minus 20 is 10, and 10 is not less than 0. So if I choose anything from this interval, it's going to fail. It's going to be false. And likewise, if I choose anything from that, it's going to be false. So the only thing that could work is numbers, x values in between negative 4 and 5. Okay, so now we're talking about polynomial inequalities, and all of these inequalities are polynomials. The difference with this example is we don't have 0 on the right? So the idea is I need to move this 6 over to the other side. It's a positive 6, so to move it I have to subtract it from both sides to make 0 on the right and get everything over to the left. So that's what I did. I subtracted 6 from both sides, and I ended up with this polynomial right here. And now I'm going to look at this and try to factor it, and it is factorable. And if I set each one of those binomials equal to 0 and solve, I get the zeros or key numbers of x equals negative 3/4 and x equals to 2. Again, I drew a number line. I popped in negative 3/4 here and 2 here. I realized that those two key numbers break my number line into 3 partitions, from negative infinity to negative 3/4, from negative 3/4 to 2, and from 2 to infinity. And keeping in mind, my inequality now is pointing the other direction, right? It's positively valued. So the positive values of this thing are going to be in my solution set. So I chose test numbers negative 1, 0, and 3. Again, you can choose any numbers you want in between those key numbers, but the closer they are to the key number, the easier it usually is to compute it. So anyway, when I plug a negative 1 in, I get a negative, right? Negative 4 plus 3 is negative 1. Negative 1 minus 2 is negative 3. So a negative times a negative, that's what this means here, equals a positive. So that means my values are going to be positive from negative infinity to negative 3/4. When I plug the 0 in, I'm going to have positive times a negative, which will give me negative. And when I plug the 3 in, I'm going to have a positive times a positive, or another positive. So, because my inequality is stating that, if this is true, the solution set has to be greater than 0, then I need to, this means positively valued, so only the places where I see a plus sign on my little wiggle graph here are going to be solutions. So if I wanted to graph this solution set, I'm going to use just a different color. Then I'm going to put a parenthesis here and shade this direction, and put a parenthesis here and shade in that direction. And all of those values from negative infinity to negative 3/4 and from 2 to infinity are going to be solutions, or will make this true. If I take any number from this interval or this interval and plug it in here, the left side will equal the right side. Okay, if I want to write it as a solution set in interval notation, well, that's easy too. All I have to do is jot down my intervals and put a union in between them. Okay. here's another one. They want you to solve and graph the solution set. So again, I've got a negative 48 over here. I need to get everything over to this side. Now this is a cubic, it's not a quadratic, so we're going to have to factor by grouping, so you have to remember that. So I'm going to add 48 to both sides to make the right hand side 0 and move that 48 over. Now here, what I did, when you're factoring by grouping, so you've got 4 terms, right? 1, 2, 3, 4. You know, you look at these two and say, gee, is there a common factor here? Well, there is, x squared. So I factored out an x squared and I wrote what was left. And then in this one over here, okay, I noticed that 16 divides evenly into 32 and 48, so I pulled out a 16 and rewrote what was left. Okay, and what I notice is, the cool thing is that if I scan this from left to right now, this factor matches this factor. So technically I'm factoring out 2x minus 3, and if I write what's left, I get x squared minus 16. So I have this factor times that factor. Okay, and now this is a difference of 2 squares, so I factored this down to x plus 4 times x minus 4, and there's not much more I can do with this, so I just brought it down. And I set each factor equal to 0 and solved, and I got x equals negative 4, x equals 3/2, and x equals to 4. And what do we do with those zeros or key numbers? We put them on a number line. Now, I have 3 key numbers here, and that means it's going to divide the number line into 1, 2, 3, 4 partitions. So you're always going to have one more partition in the number line than you do have zeros. And I noted the little intervals here, the test intervals. And so now I've got to choose a number in each test interval and plug it in to see, you know, where it's positive or negative. So I went ahead and did that. My test values are here, negative 5, 0, 2, and positive 5, right? All on opposite sides of those zeros. And I'll let you do this, but, you know, if I plug in a negative 5 here, I'm going to have a negative times a negative, which is a positive, times a negative, which is a negative. Okay, so my little interval from negative infinity to negative 4 here is going to be negative. When I plug the 0 in, which is between negative 4 and 3/2, well, I get a positive times a negative times a negative. And again, a negative times a negative is a positive, and a positive times a positive is a positive, and so this becomes positive. Okay, plugged in a positive 2, I have a positive times a negative times that positive, so that makes this interval negative. And finally, when I plug in the 5, I get a positive times a positive times a positive, so this is positive. And I go back and look at my original inequality, and I notice I need to choose values that are positively valued, right? So what that means is my solution set is going to lie between negative 4 and 3/2 and from 4 to infinity. So in interval notation, I would write it as negative 4 to 3/2 in union with 4 to infinity. And I had in class, you can barely see it on here, there's some shading, I did it like with a highlighter. But anyway, this again would be the solution set to this particular inequality. Then we've got the rational inequality. So we talked about the polynomial inequalities. Now we're going to talk about the rational inequalities, because a lot of our functions come in the form of a rational expression, a rational equation. So we can also have rational inequalities. And that's just some numerator over some denominator, where the numerator and denominator are polynomials, right? And just keep in mind that with polynomial inequalities, the only way a polynomial can change sign is about its key numbers or zeros. A rational inequality can change signs at the zeros and where it's undefined. So think vertical asymptotes. Okay. So again, I've got this example here. And just like with a polynomial inequality, you want to have the right-hand side equal to 0. So if you've got anything on the right-hand side, you need to add or subtract it to move it over, so that way the right-hand side is 0. So that was the first thing. I subtracted 3 from both sides. Now we got to use a little bit of our algebra. So algebra is going to play a very critical role in the remainder of this class because we're going to use it a lot. So the thing is that I can't combine these as they are. I can't really do anything with it. However, if I multiply this by an equivalent fraction, in other words, I want to write this as one fraction, then where the denominator of this one has to be the same as this one, right? I cannot add, so for example, if I want to add, a third plus 2/3, well, the denominators are the same, so I can write the common denominator, and then I can just add or subtract the numbers on top. So 1 plus 2 makes 3, and I can reduce that to get a 1, okay? If I want to add a third plus 4/5, now I can't do that because my denominator is not the same. I have to find a common denominator, okay? So what you can do, so over to the side here, I need this thing to have a denominator just like this fraction. So when that happens, what you do is you write the original fraction, and what you're going to do is you're going to multiply this whole number here by an equivalent fraction that contains this denominator. So an equivalent fraction means the tops and the bottom, the numerator and the denominator, are the same. So you see what I'm doing? Now if I multiply, I get 2x minus 7 over x minus 5 minus, if I distribute, so remember this is over 1, if I distribute this 3, I'm going to have negative 3x, or you can write this as plus and do negative 3x plus 15 over x minus 5. So now my denominators are the same, so I can write a common denominator, which is going to be x minus 5, and now I can add or subtract common or like terms on the top or in the numerator. So 2x minus 3x is going to give me a negative x, and negative 7 plus 15 is going to give me a positive 8. So you see, I got the same thing. I don't usually use equivalent fractions, so I just take this thing and multiply it to this. So I write the numerator that's over the denominator first, so I wrote 2x minus 7, and then I did minus 3 times the denominator back over that common denominator. And if you want me to show you in class how to do it, just remind me, and I'll go over a couple with you till you get it. So simplifying this thing, anyway, boils down to negative x plus 8 over x minus 5. And again, I'm just bringing my inequality symbol and my 0 down as I go. So this is a rational function, and the only way a rational function can equal 0 is if the numerator equals 0. So to do that, you say negative x plus 8 equals to 0. So negative x equals to negative 8. So here I'll write it over here. Negative x plus 8 equals 0. So negative x equals negative 8, and x is equal to 8. So that's the 0. Now this thing is rational, so it could have undefined aspects to it. And that's going to occur when you set the denominator equal to 0 and solve. So x minus 5 equals to 0 means that x is equal to 5. So this is a 0, and that's where it's undefined. So I treat them as key numbers. So guess what? I make a number line, and in order I put a 5 and an 8. That subdivides my number line into 3 partitions, or test intervals if you want to call it that. Okay, and then I'm going to choose again a test number inside each interval to determine whether the sign of the rational function is positive or negative, because after all, rational functions are polynomials in the numerator and the denominator, so they're still polynomials. So I chose a 4 from this interval. And if I plug in a 4, now you just got to be careful. Now you're going to use the rules of division, right? A positive divided by a negative, or a negative divided by a positive, is always going to result in a negative, okay? So you see, here's one and here's another one. It doesn't matter if the plus or the minus is upstairs or downstairs. If the signs are different, top and bottom, you're going to get a negative result. So what I know is when I plug the 4 in, I got a negative 4 over a negative, I got a positive 4 over a negative 1. So I have a positive divided by negative, so that's going to give me a negative value. when I plug in the 6, I'm going to have a positive 2 over a positive 1. That's a positive divided by a positive gives you a positive. And then when I plug the 9 in, I'm going to have a negative divided by a positive, which is going to give me a negative. All right. And my inequality states less than or equal to, so I know that my solution set is going to have to be those values that are negative. So if I'm to graph this thing, I'm going to go to 5 and put a parenthesis and go like so, and I'm going to go to 8 and put a bracket and go like so, and I'll tell you about that in a second. Interval notation, I can write as negative infinity to 5 and union with 8 to infinity. Now the bracket means I can include the 8. Why? Why can I include the 8 and not the 5, let's say? Well, I can plug an 8 here and get 0 over 3. 0 over anything is 0. So that's okay, that's not a problem. It's division by 0 that's a problem. So if I plug a 5 in here, I'm going to have something divided by 0, and that's bad. So I cannot include the 5 in the denominator, but I can include the 8 from the numerator. So we use the bracket to include it. That would be the graphed solution set, and in interval notation, like I said, you would have that there. Okay, so your homework was to complete those problems. So give them a try if you were absent during the lesson and whatnot, and we'll talk about them during our review tomorrow. Hope you have a good night.